Hello, everyone. Welcome to this session, first session on embodiment. That is obviously a rising question in virtual reality. So I won't take much time saying that it's a new adventure for all of us. So welcome again, and I will introduce the first paper by Tabitha Peck from Davidson. And she's an assistant professor of mathematics and computer science. And she will present about a topic that is already a hot topic today about underrepresentation of female participants in virtual reality research. Tabitha, it's up to you.
Virtual reality applications are diverse and can include exposure therapy for fear of heights, military training, pain management, and disaster management training. Virtual reality users are also diverse across age, physical ableness, race and ethnicity, and gender. The development and evaluation of VR applications for this diverse set of users often follows user-centered design practices. In the last 5 years of papers published at IEEE VR, 82% of the manuscripts reported results from human subjects user studies. We are interested in investigating the population of users studied in IEEE VR manuscripts to determine if they are representative of the diverse set of potential virtual reality users across the globe. During this presentation, I will use the term gender, defined as the socially constructed expectations for behaviors, characteristics, and roles considered appropriate for women and men. This includes male, female, gender fluid, agender, and more. We discuss the demographics that were reported in manuscripts where all participants were identified as either male or female, except for one participant who was identified as transgender. During this presentation, the blue icon will represent male participants and the red icon will represent female participants. We collected data from the last 5 years of IEEE VR. This included 325 manuscripts that reported results on 429 studies. Collected data included the manuscript type, journal or conference, the number of participants, including the proportion of female participants, the average age of participants, and the number of authors, including the gender of the first author and the proportion of female authors. To limit data entry errors, each manuscript was checked by at least 2 people. When determining manuscript author gender, we performed internet searches, looked at LinkedIn accounts, and university websites. Previous research suggests that misclassification rates are approximately 0.3% when using internet searches to identify author gender. Additionally, the data can be downloaded from GitHub. The participant analysis was performed with the data from 319 out of the 429 total studies published at IEEE VR from 2015 through 2019. Studies were excluded due to not collecting data from human participants, not reporting the number of study participants, or not reporting gender demographics. The general population of the world is approximately 50% men and 50% women. An underrepresentation of women and girls in VR research would be evident by significantly fewer female participants compared to male participants. Each glyph represents 50 participants from user studies at IEEE VR over the last 5 years. During this time, there were 3,684 female participants and 5,873 male participants. The median number of male participants per study was 13, while the median number of female participants was significantly fewer at only 7. This supports our first hypothesis, that female participants are underrepresented in human subject VR research compared to male participants. We next investigated the hypothesis that female authors are underrepresented in VR research compared to male authors. The author analysis was performed with the data from 320 out of the 325 published manuscripts. Manuscripts were excluded if one author gender was not identifiable on the paper. 323 manuscripts were used in the first author analysis. During the last 5 years, only 16% of authors were women. This underrepresentation may be partially explained by the underrepresentation of women obtaining PhDs in computer science. However, virtual reality research is interdisciplinary and includes other disciplines like human-computer interaction or psychology, where women are not underrepresented. Not only are women underrepresented, but they are not part of the research. The median number of male authors per paper was 3, while the median number of female authors was 0. This means that fewer than 50% of papers had female authors involved in the research. This supports our second hypothesis, that female authors are underrepresented in VR research compared to male authors. This is troubling, since previous research has shown that diverse research teams are more innovative, creative, and productive compared to non-diverse research teams. We also considered the relationship between authors and participants. We hypothesized that there are a greater number of female participants in studies in papers with female authors compared to papers with exclusively male authors. We compared the proportion of female participants reported in papers with the number of female authors on the paper. For papers with no female authors, 34% of reported participants were female. However, when a paper included at least one female author, the proportion of female participants rose significantly to 41%. This supports our hypothesis that there is a greater number of female participants in studies published in manuscripts with female authors compared to participants in studies published in manuscripts whose authors are exclusively male. We further investigated if the underrepresentation of female participants were potentially biasing results in VR research. Let's assume that there are no VR measures related to the proportion of female participants in a study. If this is true, we can continue using participant samples with significantly fewer women and girls compared to men and boys. Let's consider the common measurement of simulator sickness. It is relevant for all VR experiences, and previous research has found gender differences in simulator sickness, but differences are not seen in all studies. Finally, there is a standard simulator sickness questionnaire, making it easier to compare results across studies. In human subjects design experiments, data is collected from participants and then an effect size, a quantitative measure of the magnitude of the experiment effect that emphasizes the size of the difference between two variables, is then calculated on that population. In a meta-analysis, instead of collecting data from individual participants, standardized effect sizes are collected from individual studies that meet predefined criteria. These effect sizes are then weighted and combined to produce an estimate of the average effect size across the set of studies. The studies included in our meta-analysis presented results of an empirical study of human subjects. The study participants were exposed to an immersive virtual environment using a head-mounted display. The study assessed simulator sickness before and after virtual reality exposure using the Kennedy Simulator Sickness Questionnaire. The manuscript reported data for the calculation of an effect size representing the average within participant change in simulator sickness. And the manuscript reported the number or proportion of female participants. 22 of the 429 studies met our predefined data criteria and were included in our meta-analysis. The results of our meta-regression can be seen in the following bubble plot. Each dot is a study that met our predefined criteria. The y-axis is the study level effect size, and the x-axis is the proportion of female participants included in the study. This is redundantly encoded with the color of the circle. The size of the circle is proportional to the precision of the effect size of each study. Precision encompasses variance, standard error, and confidence intervals, and is affected by both the sample size and study design. As the proportion of female participants increased, we observed smaller increases in simulator sickness following VR exposure. The overall effect size indicates that, on average, participants in VR studies using HMDs experience small but significant increases in simulator sickness after VR exposure. However, this outcome was systematically related to the proportion of female participants included in each study. This finding is surprising, as some studies have found evidence that women are more susceptible to motion sickness. However, it is important to note that the study-level findings of this meta-analysis do not necessarily indicate that individual female participants reported smaller changes in simulator sickness. We further investigated if any other moderators, including manuscript type, participant age, or first author gender, were significantly associated with the observed effect sizes of each study. The proportion of female participants was the only significant moderator. This demonstrates that our original assumption was false, since there is at least one VR study measure, simulator sickness, related to the proportion of female participants in a study. Further, our results provide evidence that continuing to collect data from participant populations where women and girls are underrepresented may result in biased findings. To limit biased findings, when developing VR hardware and software for a general population, an equal proportion of male and female participants must be used. With data collected from the last 5 years of IEEE VR, we were able to support all 3 of our hypotheses. That female participants are underrepresented in human subject VR research compared to male participants. That female authors are underrepresented in VR research compared to male authors, and that there are a greater number of female participants in studies published in manuscripts with female authors compared to participants in studies published in manuscripts whose authors are exclusively male. We also demonstrated that the underrepresentation of women and girls as participants is biasing results by showing that there is at least one VR study measure related to the proportion of female participants in a study. This indicates that there may be more measures that we are unaware of. VR applications and users are diverse. If we are designing with the intention that everyone will use virtual reality, then we must test and design for all of our intended users. As researchers, we must commit to using samples that are representative of the population for which the technology is being designed. When we are developing for the general population, we must collect data from populations that are approximately 50% women and 50% men. As authors, we must include demographic information in our papers so that readers can accurately interpret the population that was studied. And finally, as reviewers, we must provide appropriate constructive criticism and advice when papers making general claims do not use a participant sample that is representative of the population. As a community, by committing to these simple changes, we can produce higher quality scholarship and develop virtual reality applications for everyone.
Thank you. Okay, thank you for this quite informative talk. I got echo here. Sorry. A few questions. One question. Do you think this work could support a higher level? I got echo here, I'm sorry. Hypothesis that the subject pool of most human subject research is dependent on the social circle of the authors.
I'd say I think that is actually part of the current concern, is that a lot of times these studies are looking at convenient sampling. I admit that I've done this myself. Of trying to recruit people from my own labs back in graduate school. And so one of the concerns is that we are recruiting from this smaller set of people and only recruiting from our own graduate student populations. And if we reach a broader collection of people, recruit from the general population, this was also suggested by John yesterday during his talk, that we would be able to make higher level hypotheses to include larger groups of people because our samples would include larger groups of people.
Second question. Can the author elaborate more about how the search to determine author gender was performed?
Yeah, so the way that we determined author gender was that we performed internet searches, so it was whatever was publicly available on the internet, using university websites, LinkedIn accounts. And so it was only what people had chosen to make publicly available is what we used. And we've also made the data available via GitHub, so that if we did make errors, we would want to know that so that we could correct those in the future. But also previous research has shown that performing these internet searches to determine author gender produces very few errors, with 0.3% of errors on the data collected.
Okay. Am I muted yet? Can you hear me?
Yes.
Okay. One more question is, let me get to that. Do you think these results of yours are related specifically to VR research or more generally to computer science research?
I think they're related to all research involving human subjects. So anytime that we're collecting data where we're designing for people, we're collecting data from people. And so any research that is looking at determining how to design for a group of people, an important thing to consider is who are you actually designing for? If you're designing something where you intend everybody to be able to use it, then you need to consider everybody during your design process.
Okay. I suspect we have to move to the next talk now. All right. And thank you. But I introduce you again. So for the next talk, which is about the impact of self-avatar, hand collocation, and hand proximity on embodiment and Stroop interference. Up to you.
Our hands are critical for interacting with and manipulating real-world objects. Previous literature shows that the proximity of our hands to objects has numerous benefits. It has been demonstrated that proximal hands improve short-term memory, enhances cognitive control, and triggers the action-based cognitive pathways. Earlier research also supports that one's own hands is not necessary to replicate the proximal hand effect, regardless whether the user's own hands or a rubber hand. Visually seeing a hand proximal to a cognitive task is shown to improve cognitive performance compared to non-proximal hands. When users get into a virtual environment by wearing a head-mounted display, their physical hands are obscured from their view. To fix this problem, virtual reality designers and researchers provide virtual hands for the user. These hands are used for tasks that require cognitive control, short-term memory, and other important cognitive functions. It is currently unknown how the proximity of virtual hands to objects affect cognitive performance. When a visual self-representation of one's hand is provided, a self-avatar is used within the virtual environment. Previous research shows that self-avatars come with many benefits for the user. It has been shown that providing a self-avatar increases self-presence, enhances distance estimation, and improves cognitive performance. Knowing that physical hands are important for cognition and object manipulation, and self-avatars are shown to improve cognitive performance, we investigate the following two questions. Can we replicate the effect of proximal hands on cognitive load in virtual environments? And can the presence of a self-avatar mediate the effect of proximal hands on cognitive load? To investigate these questions, we have formed the following four hypotheses. 1. Self-avatars improve the user's sense of embodiment. 2. Users with co-located physical hands have a higher sense of embodiment compared to users whose physical hands are not co-located with the self-avatar's virtual hands. 3. Physical hand placement affects Stroop interference. 4. Users with a self-avatar with proximal hands have mediated Stroop interference regardless of physical hand placement. In the rest of this talk, we will introduce our experimental design. Under experimental design, we will discuss our measures. With our first measurement, embodiment, we'll show how we test our first and second hypotheses. And with our second measurement, Stroop interference, we'll show how we're testing our third and fourth hypotheses. Then we'll talk about the procedure. The procedure is followed by results in regards to embodiment and Stroop interference. And finally, we'll finish up with our conclusion. Our experimental design. We've designed a 2x2 between subjects study. As seen in the figure, a user can either have proximal or non-proximal hands, and can either have a self-avatar or not. We recruited 60 participants for this study, with 1-to-1 female-to-male ratio. Every user is randomly assigned to one of the 4 conditions shown in the figure, with the constraint that every condition has an equal number of users. For the rest of the presentation, we'll follow the same coloring scheme to represent the experimental conditions. The light blue represents the non-proximal avatar condition. The dark blue represents the proximal avatar condition. The light green represents the non-proximal no avatar condition. The dark green represents the proximal no avatar condition. Users in the proximal hand condition have their hands nearby the cognitive task. In the non-proximal condition, participant hands are on their laps, far away from the cognitive task. In the avatar condition, participants are given an avatar that has its hands proximal to the cognitive task. And finally, in the no avatar condition, participants are not given an avatar. Our first measure, embodiment. Sense of embodiment is defined as the ensemble of sensations that arise in conjunction with being inside, having, and controlling a body, especially in relation to virtual reality applications. To measure embodiment, we use the Gonzalez-Franco-Peck 7-point Likert scale embodiment questionnaire. Users answered questions regarding ownership, agency, tactile sensations, location, and appearance. Finally, we combine all of these submeasure scores to form an overall embodiment score. Our second measurement, Stroop interference. Stroop test measures working memory load, which is defined as the short-term memory that retains small amounts of information in readily accessible forms. In our Stroop test, a fixation cross appears for 1500 milliseconds. This fixation cross is followed by either a congruent trial where the color of the text matches the color written on the text, or an incongruent trial where the color of the text does not match the color written on the text. Procedure. When the user enters the virtual environment, every user enters the embodiment phase. A user is either given a self-avatar or not. In the virtual environment, there's a mirror in front of the user. Every user is asked to look around the scene, look up and down at their hands, and explain what they see for a minute. After the embodiment phase, the experiment continues with 6 practice trials, where the user learns how to respond to the Stroop test correctly. In the second practice trials, the experiment continues with 20 practice trials, which exactly follows the same format as the experimental trials, where 80% of the trials are congruent and 20% are incongruent. Then, the users go through the experimental training blocks of 200 trials, during which we collect our Stroop data. Finally, a user finishes with answering the embodiment questionnaire. Embodiment results. In this box plot, we have embodiment scores on the y-axis and our experimental conditions on the x-axis. We found a significant difference between embodiment scores of users with an avatar and without an avatar. The significant difference supports the first hypothesis that users with a self-avatar have a higher sense of embodiment compared to those that do not have a self-avatar. To test our second hypothesis, we compare embodiment scores in the avatar proximal and non-proximal conditions, and we can confirm that there's a significant difference between these two groups. This supports our second hypothesis that users with the co-located hands have a higher sense of embodiment. Stroop interference results. When we compared the Stroop percent accuracy rate, we found that participants were less accurate on incongruent trials compared to congruent trials. This supports the earlier literature. When we investigated Stroop accuracy rates by trial types and hand location, we found a significant difference between incongruent and congruent trials in the non-proximal condition, regardless of avatar presence. However, we found no significance between incongruent and congruent trials in the proximal condition. With this, we can support the third hypothesis that physical hand placement mediates Stroop interference. Contrary to what we hypothesized earlier, we found no significant avatar effect. With this, we can say that we were unable to support the fourth hypothesis, that the presence of a self-avatar with proximal hands mediates Stroop interference. Finally, our conclusion. Our results show that hand proximity to a task affects cognition in virtual environments. This also replicates the earlier literature. Surprisingly, our results show that self-avatars do not mitigate Stroop interference. We also found one example where the existence of a self-avatar does not positively affect performance in a virtual environment. Finally, this does not replicate previous research that seeing in hand would improve cognitive performance. Thank you.
Thank you. Thanks a lot. I think Talisa is going to take questions. I don't see any question on the board. So I got one. So why use the Stroop interference task better than other tests for dual task?
So why use Stroop interference instead of some other working memory task?
Yeah.
We wanted to try Stroop interference. It's a relatively common test that people know and have used in virtual environments before. And so we decided to try that one and see the results. However, I think some interesting follow-on work to this would be to look at some of the other standard working memory measures like the NBAC task.
All right. Do we have other questions from our speakers? All right.
It
No,
looks like one just appeared.
I'm sorry?
It looks like one just appeared on Slido.
Slido, yeah, I gotta go to that. What is the difference between the iconic and real hand? Only the color?
So in the conditions where participants had an avatar, their avatars were gender and racially matched with the participant. And so, yes, they were different hands because they were avatar hands, but they still should have been similar to the participants' real hands. The big difference is that the avatar hands were always placed on the desk next to the Stroop interference task, where the participants' hands could have either been on the desk or on their lap. And the surprising result in our minds is that regardless of that avatar, it was the participants' hands that were the only effect for the Stroop interference, not the avatar.
Okay. I was just, since I have some time, I was just wondering about, I know recent work on, this experiment, Gorilla in the Mist, I guess.
I'm sorry, which experiment?
Gorilla in the Mist, where you have these people playing handball, passing balls, and there's a gorilla crossing the room. You know this experiment?
Yes.
I was wondering if this could be an interesting idea to test on your kind of task. But how people give attention to what's happening beside the main task. I mean.
Yeah, no, so I think that that's a really interesting area. I know there's some work in terms of change blindness and kind of distractions in terms of how you can kind of manipulate the virtual environment due to those attention-based tasks and kind of distracting people during the environment. So yeah, I think that that's an interesting area to follow.
Thank you. Nice work anyway.
Thank you.
I guess, yeah, we're going to move to the next talk, presentation, whatever. It's presented by Rebecca Fribourg, I would say. Freiburg. She's a PhD student in virtual reality in Rennes, France, at INRIA Research Center. And she's going to present us work on avatar and sense of embodiment, studying the relative preference between appearance, again, control, and point of view. Rebecca.
Okay, hello everyone, and thank you for attending this live presentation about our study on the relative preference between appearance and control of an avatar, as well as users' point of view towards it. It's a work that has been done in collaboration with Sarah Narget-Laguet, Anatel Lécuyer, and Ludovic Oyer. And I will directly start with some context. So in the past years, many studies have tried to better understand how users perceive their avatar in virtual reality by studying the sense of embodiment. And more precisely, they focused on three subcomponents. Firstly, the sense of self-location. That would be the sense of one special experience, of being inside a body. Then the sense of agency, that would be the sense of having global motor control over a body, and the sense of ownership, that would be one's self-attribution of a body. And from this research emerged different factors of influence towards these three subcomponents. For instance, the avatar appearance that can be modulated with general structure, shape, dimension, or rendered style. And in the literature, it was shown to be highly linked with the sense of ownership, saying, for example, that the more realistic an avatar would be, the higher the sense of ownership would be. Then we have the avatar control that can be either recorded animations played on the avatar, partial body tracking mixed with inverse kinematics, or full body tracking. And in the literature, it was strongly linked with a sense of agency, showing that good visual motor feedback would give high sense of agency, while discrepancies in the visual motor feedback would decrease it. And then we have users' point of view that can be modulated with the camera placement from either first-person point of view to different kind of third-person point of view, depending on the camera placement and angle. And it was linked in the literature with the sense of self-location, showing that the sense of self-location was higher in first-person point of view, but that it was still possible in third-person point of view with synchronized stimulations. So from the related work, it seemed that we have those three main connections. Yet, it is not that simple. The avatar appearance was also shown to have an influence on the sense of agency. The avatar control also influenced the sense of ownership, and users' point of view also influenced the sense of ownership. So in the end, due to all possible interconnections between the factors influencing the sense of embodiment and its subcomponents, it remains challenging to quantify the impact on the perceived sense of embodiment as a whole. Then, the interrelations between the factors influencing the sense of embodiment remain uncertain, which is why we ask ourselves this question. Are there factors which have a higher influence towards the sense of embodiment? And to answer this question, we conducted a subjective matching experiment that I will now detail to you. So this experiment is inspired from a method used in color science, in which individuals observe a color and then try to match it by additively mixing the three primary colors. It has been applied to the study of the sense of presence in virtual reality. And we propose to apply it for the first time to the context of the sense of embodiment, where users tried to match a given sense of embodiment by combining different levels of appearance, control, and point of view. To do so, we then have to define different levels for each factor that could all be combined together. So for example, for the appearance, we had for the lowercase a very minimal avatar with abstract spheres, and we could have at the maximal personalized avatar, realistic avatar. So we didn't have a proper scanning solution, but a participant could pick in a list of avatar the one that they think looked like them the most, and then we could personalize the avatar shortly in terms of hair and cloth colors. Regarding the control, it could be at the minimal some automatic recording animation played on the avatar of the participants, so with no control from the participants. And at the maximal, we had some motion capture solution using the Xsense system. And then we only had two levels for the point of view, third-person point of view that you can see in this picture, and the first-person point of view on the right. We conducted a baseline experiment allowing us to reduce the number of levels, keeping only levels perceived significantly different. So I won't detail this experiment now, but if you want to have more information, you can look into the paper. And so in the end, we were able to keep only 4 levels for the appearance, 3 for the control, and 2 for the point of view. And then we have defined 4 different tasks for our main experiments, all in the context of a fitness room. So firstly, we have here the punching task that involved more the upper body of the participants, in which they had to punch a punching ball. We have the soccer task then that involved more the lower body of the participants. We had a walking task that is not lunch, but it's not a big deal. Maybe I can try here. No. It's okay, in which participants had to walk and avoid obstacles. And we had a fitness task in which participants had to mimic the movements of a virtual character in the room. So it was a mixed design, meaning that each participant performed only 2 of the 4 tasks. And for each task, here was the protocol. User tried, firstly, the optimal configuration of an avatar considering our baseline experiments. So it consisted in a first-person point of view, a full body motion capture using the Xsense that you can see here, and a personalized realistic avatar. And they were asked in this configuration to remember the sense of embodiment in terms of how they felt they owned the body, that they controlled it and felt spatially inside it. And then they would also try all the levels. Afterwards, each participant started once from each of the minimal configurations. That could be either all the level at 0 or one level, all the level at 0 except 1. So here we have, for example, the appearance and the point of view that are at the minimal level, but there is some degree of control of the avatar. And then with this first configuration, they performed the task and were asked afterwards to increase 1 level of either the appearance, control, or point of view. And then they would perform the task again and keep on going by improving levels of factors and testing the task again. So in the end, for each task and participants, we could have some graph and some path of choices drawing inside it. So I will just show you a little example. So let's see that one participant started in the minimal configuration with all level at 0. So you can see at the same time what it looks like here. So there is no control. The animation is launched automatically on the avatar, and the appearance and point of view at the minimal level. And then, so he performs the task and is asked which level does he want to increase now. So let's say he increases the control. So now none of the other level factors have changed, but there is more control. So he can actually now kick on the ball. Afterwards, he may say that he wants to increase the appearance now because it feels like he needs to increase this factor to reach the sense of embodiment that he had experienced initially. So you can see here in the video that you are now a stickman avatar. And he may decide afterwards to go into a first-person point of view that you can see also in the video. At this point, the participant may say that the sense of embodiment he experiences in this configuration is equivalent to the one experienced in the optimal configuration, because participants were asked to tell the experimenter each time they would experience an equivalent sense of embodiment. And we called this configuration in which it occurs accepted configurations. So to sum up regarding the design, we had two dependent variables, the probability of increasing a level of factor given a configuration, and the accepted configurations. And we had three main hypotheses. First, that we will observe that some factors will be prioritized over other factors. Two, that other configurations will elicit equivalent sense of embodiment as in the optimal configuration. And three, we expect the task to have an impact on the results. So let's look into it. We computed Markov chains for each task to visualize probability of choices from one configuration to another. So I won't go into detail of all the graph for all tasks, but I will firstly focus on the first choices made by the participants, the initial increment of levels. So we have here all the tasks, and what we can see is that for all tasks, the control and the point of view were highly preferred in terms of improvement for the first choice compared to the appearance, which had a low probability of being improved in the first place. So it's also visible in some subjective ratings that we get from post-experiment questionnaires, where we asked participants to rate their preference, their overall preference over the three factors, and control and point of view factors were significantly rated higher than the appearance. So it's interesting, actually, because avatar appearance has a big impact on ownership. And yet, when users are asked to choose between appearance and other factors, they seem to prioritize the other factors. And then we had the accepted configuration. So as a reminder, we were interested in the accepted configuration, which are the configurations in which participants felt an equivalent sense of embodiment as in the optimal configuration. So let's have a look at this graph that shows the probability of configurations to be accepted. And what we can see is that the configuration 1-1 had a high probability of being accepted for the tasks soccer, fitness, and walking. What is also interesting here is that it was not the case for the punching bag task. So it may be, so it means that it seemed to mean that for the punching tasks, the participant needed higher level of appearance to feel an equivalent sense of embodiment as in the optimal one. It can be because in this task, people had more cues of their upper limb compared to other tasks, and it may have had an influence on the results. So this difference between tasks is also visible in other results that we have. So, for instance, we computed the best path graph for each task, which combine the paths that are the most likely to be taken by participants. And what we can see is that for the soccer task, the control have been at several points prioritized over the other factor. So a possible explanation for that is that in this task, there were results like the ball going into the goal or not. So it could be an explanation why the control was really important. But also what is interesting is that the only difference between like the participants always wanted to reach a higher level of control, which was motion capture against inverse kinematics. So it's interesting that in that case, this incrementation was important. And then we have a big importance of the point of view for the walking task, which we can see here in the first choice, where the point of view was always increased first. It might be because in this locomotion task, participants may have preferred to look to have more visibility on the ground, which is maybe better with the first person point of view. So to sum up the results, we showed that the point of view and control factors were preferred when trying to reach a given sense of embodiment, which validates H1. We highlighted some accepted configurations in which participants felt equivalent sense of embodiment as in the optimal one, which validate H2. And we found that the task had an influence on the results, which validates H3. So I will now conclude very shortly because I don't have much time left. So it was the first subjective matching study assessing the relative contribution of these three factors on the sense of embodiment when performing 4 distinct tasks. And it highlighted insights about which factors to prioritize in order to enhance the sense of embodiment towards an avatar in different tasks, and about configurations which lead to fulfilling sense of embodiment in virtual environments. Regarding future work, so in our contribution, the choice level were constraints, mostly for technical reason. So it will be very interesting to explore more levels. So for example, for the appearance to reach the scanning avatars fidelity, for instance, and also to explore different third-person point of view with different position and angle of cameras. It would be very cool. We also had limited choice of factors. It would be very interesting to go into more kind of factors, for instance, multisensory feedback with haptic feedbacks and things like that. And also we have no certainty that the sense of embodiment was the same when they said they had the equivalent sense of embodiment. So it would be actually interesting to mix this study with more subjective tests and try to compare the choice of participants with that, even though it would add more time to the experiment. So that's it for me. Thank you for your attention. And if you have any questions or feedback, I'm ready to hear them. Thank you.
Okay.
Okay.
All right. Okay.
Okay. I've stopped sharing my screen, though.
Yeah. Am I good? All right. Thank you. Thanks a lot, Rebecca, for being live, remotely live, which is some courage. I appreciated your talk. This is a fascinating methodology. And if I dare comment, I'm always impressed by people in Rennes mastering experimental science so nicely, I would say. So one first question would be from my part is, how do you deal with variability between the subjects, and how many subjects did you test in this experiment?
So it was 40 participants in this experiment. 20. I mean, there were 2 experiments, but I will actually focus on the main one, not the baseline, but the subjective one. So 40 participants, 20 women and 20 men. And so I must say that variability between participants is quite a subject at the moment. We discuss it a lot with some colleagues, and we have not tried really to address this in the paper, but we have conducted also in Rennes an experiment trying to find correlations with personality traits of participants with the way they would perceive the environment. And well, it's definitely something that interests us, for sure, variability within the participants.
One more question is, you use, as many people, this mirror trick to enhance embodiment.
Yeah.
I have trouble with that because is this first person or third person viewing?
Yeah, but this is a really, it's a good question because we hesitated so much in this experiment to put it or not, because indeed, like, and also because we're switching from third person point of view. So in that case, what was the third person point of view with the mirror? I don't know, but still, like, it seemed to be appropriate. It seemed to enhance, especially with the low field of view of the HMD, where you cannot see that much your own body. It seems to improve a lot the sense of embodiment you may have towards your avatar. So we keep on using them, though. But I understand. I know that in subjective questionnaires they try to divide the questions regarding the mirror and regarding the own body to try to assess this problem.
Yeah, it's an interesting question. A few questions from the audience. Let me get to that, if I can. Wait. Are the results dependent on the participants' understanding of what is a sense of embodiment?
Yeah, so, sorry. Is it the end of the question?
No, the question was, how did you ensure that all had the same understanding, which is the
okay,
same
yeah.
question.
Okay. It's a very good question. So we, of course, like when we explained this to the participant, we made sure like they had no question and they understood, but still we don't have any proof that they all understood the same the question. So actually, one comment we had from the reviewers of the paper was that the questions we asked to the participants could maybe be a bit improved to ensure that all the participants ensure it's the same way, because we tried to define it a little, but still there is some improvement to do to ensure that all participants have understood the question. It's definitely something to improve in this method.
Next question is great speech. I like the approach you had between with the different embodiment parameters. Did you think about adding visual tactile stimulations?
Yeah, that would be great for sure. It's just like the problem with this method is that all the factors and levels have to be combinable. So that's the trick. Sometimes we want to add something and then we realize, no, like if you are with these levels of factors, like you cannot have, it doesn't make sense. So for sure, it would be really nice, like to add more levels and factors, but it's just something to configure, but it would be really great.
Okay. If I have time, two more questions. It looks like your graph is acyclic. Could the participants move back and forth between conditions?
I'm not sure I understand, like when they're trying to improve, if I am correct, like could they go back well, I won't get, I guess, the reply from that. But so if I understood correctly, so no, the participants, like when they made a choice of improvement, they could not go back. That's why we like showed them at the beginning of the experiment, we showed them all the levels so that they would be quite aware of all the possibility of improvement they would have.
Yeah, thank you. The last question is, are the tests validated with different range of age people? Does it change with aging?
I actually don't think I have checked that, but that's something I could check, but I have not checked influence of age regarding the results.
Yeah. Okay, thanks a lot. I guess we have to move forward. Thanks to you.
Thank you.
The next talk is by Nami Ogawa from Tokyo University. I guess she's a PhD student with Dr. Hirose, and she will present about the effect of avatar appearance, again, on detection thresholds for remapped hand movements. Nami, it's up to you.
Hello, I'm Nami Ogawa, a PhD student at the University of Tokyo. Virtual reality researchers have developed a number of interaction techniques where users' physical hand movements are remapped onto different virtual hand movements. For example, haptic retargeting and redirect touching create a discrepancy between the position of the real and virtual hands to effectively provide passive haptics. Such techniques are called as hand remapping techniques. A common challenge in the hand remapping techniques is that when the offset between virtual and real hands increases, users become aware of the remapping. According to prior research, the detection threshold for the horizontal and vertical linear remapping are estimated to be only up to 4.5 degrees in any directions, which are quite narrow ranges. The purpose of a study was to investigate if representations of the virtual hands affect the detection threshold for the hand remapping to address this challenge. Now I'm going to explain why we focused on virtual hand appearances. In the first place, why does hand remapping work despite hand displacement? The hand remapping techniques are typically explained by visual dominance over proprioception. However, it can be also said that these are a type of body ownership illusions, where a virtual hand is felt as one's own hand, and the virtual and real hands move correspondingly. Now let me briefly explain the mechanisms of body ownership illusions. The sense of body ownership emerges from a combination of top-down and bottom-up processes. The top-down factors refer to appearances of a virtual body. Previous studies have shown that the closer the appearance of the virtual body is to our own bodies, the stronger the sense of body ownership. On the other hand, the bottom-up factors refer to synchronous multisensory or sensorimotor stimuli. So the displacement between the real and virtual hands weakens the body ownership illusions because vision and proprioception become incongruent. The point is that, regardless of the amount of hand displacement, the strength of the body ownership can still be manipulated by the avatar appearances in top-down processing. However, hand remapping techniques have rarely been associated with the body ownership illusions. Ownershift was the first study to mention the importance of the body ownership illusion in a hand remapping technique. The authors considered the sense of body ownership to be a requirement in the technique they proposed and evaluated the sense of body ownership. In contrast, our idea was to find a factor that accounts for the sensitivity to the hand remapping based on the evidence from the body ownership illusions so that we can improve the hand remapping techniques regardless of the mapping algorithms. These backgrounds have motivated us to investigate how avatar appearances influence the sense of body ownership and the detection threshold in the hand remapping techniques. Realistic virtual hands have shown to increase the sense of body ownership, but it's still unknown how much they affect when hands are remapped, so we investigated. In addition, we hypothesized that realistic virtual hands can also make their mapping less noticeable by fostering the sense of body ownership over the remapped hands because both are a matter of self-attribution. Compared to the effect on the body ownership, this hypothesis is not necessarily obvious because the detection thresholds are related to the self-attribution of a movement or the sense of agency. So we conducted an experiment. The experiment mainly consisted of two tasks, namely a remapping detection task and a self-localization task. The main task was the remapping detection task, which measured how sensitive participants were to the remapping. On the other hand, the self-localization task was conducted to measure the proprioceptive drift, which is the displacement of proprioceptive self-localization toward a virtual hand from the actual hand position. This is an established objective measurement of the strength of the body ownership illusions. Regarding the remapping model, we use the horizontal linear remapping because it's a common and basic form of the hand remapping. The experiment was conducted with 16 right-handed participants, and all the tasks followed as within subject's design. We used Oculus Rift CV1 as a head-mounted display and lip motion controller to track the participants' hand movements. Let's look at the mapping detection task first. In each trial, the participants reached for a virtual button with their right virtual hand, which is horizontally remapped. Then they judged if the movement of the virtual hand exactly matched the movement of their own hand in two alternative force choice tasks. The shift amount, which was defined as the distance between real and virtual hands when the virtual hand reached the button, was varied between trials according to a staircase procedure. For example, when the participants answered no to the question, which meant that he or she was aware that the movement was remapped, the staircase algorithm reduced the shift amount for the next trial. By repeating that, the staircase method can efficiently find the detection threshold. In half trials, the virtual hand was replaced by a virtual sphere. It's an abstract avatar. In addition, the detection thresholds were estimated for each shift direction. Finally, the staircase algorithm needed 28 trials to converge for each condition. Here's the actual setup. The participant reached for the button and answers whether the movements of real and virtual hands exactly matched. Now let's move on to the self-localization task. The participant first reached for a virtual button as with the mapping detection task. But when the button was pushed, the virtual hand and the button disappeared. Then the participants estimated the position of their actual index fingertip. Let's say the perceived proprioceptive position is here. The participants answered this position by shifting the virtual board using a control held in their left hand. During the estimation, they had to hold the position of the real hand. The proprioceptive drift is defined as the distance of the actual position to the estimated position. Each participant conducted 40 trials. They consisted of 2 avatar appearances and 5 shift levels from -10 to +10 centimeters. Please remember that the shift direction is from real to virtual, so the positive values indicate the rightward shift. And lastly, a trial for each unique condition was repeated 4 times. Here's the actual setup. She reached for the button and answered her actual index finger position by shifting the board position. The conditions for the 2 tasks can be summarized like this. In addition, we conducted a heartbeat counting test to assess interoceptive sensitivity, which has been shown to predict the susceptibility to the body ownership illusions. So we expected that interoceptive sensitivity may also account for one's sensitivity to the remapping. Furthermore, the subjective sense of embodiment was assessed through a questionnaire. However, I'll leave out the details regarding these tests today, so please read our paper for details. Let's take a look at the results. If you look at the detection threshold for each condition, you can see the significant difference between realistic and abstract avatars for leftward shifts. In fact, we found a statistical difference between these numbers as a result of a two-way ANOVA and Turkey's post-hoc tests. In addition, when we calculated how much the realistic avatar increased the detection threshold compared with the abstract avatar for each participant, we found the threshold with the realistic avatars to be 31% higher on average for leftward shifts and all the participants had a positive ratio, which meant that the effect of avatar appearances was applicable to anyone for leftward shift. As for the proprioceptive drift, we observed a very similar trend. As I explained earlier, the proprioceptive drift is defined as a bias from real to virtual hand positions. What we were interested in was the effect of avatar appearances, that is, the differences between orange and green plots. So please take a look at these asterisks. With abstract avatars, the proprioceptive drift hardly occurred. In contrast, with realistic avatars, the proprioception was drifted to the virtual hand position. To summarize, these results show that compared with an abstract avatar, the realistic avatar makes the remapping less noticeable and brings the proprioceptive hand position closer to that of the virtual hand in case of leftward shift. In other words, realistic avatars can foster the self-attribution of movements as well as the self-attribution of a body. In addition, even though the proprioceptive drift is considered to be a measurement of the strength of the body ownership illusions, it indicates that when realistic avatars are used, visual information is given greater importance in visual proprioceptive integration as compared to abstract avatars. So why is the avatar appearances effective only in the case of the leftward shift? To answer this question, we may first consider what was different between left and rightward shifts in essence. In fact, they were not symmetric against body midline in terms of real hand movements because the participants used the right hand. When you try to reach out your right hand for each direction, you will notice that how muscle was used was totally different, and you might feel a change in the sensitivity to the proprioception. In addition, when leftward shift is applied, the hand moves in the direction away from the body midline. The distance from body midline has been said to influence the body ownership illusion because it is related to the peripersonal space, which fosters multisensory integration. Probably because of these differences, our results in fact showed anisotropy regardless of avatar appearances. The detection thresholds and the proprioceptive drift were both lower for leftward shifts than for rightward shifts on average. So we consider that the realistic avatar fosters the self-attribution of a body and movements when the visual proprioceptive integration hardly occurs. Future work includes to further strengthen the sense of body ownership by means other than avatar appearances, such as adding synchronous visual tactile stimuli like passive haptics to further increase the detection thresholds. Another interesting prospect is to dig deeper into the effect of avatar appearances. For example, it is known that a stronger sense of body ownership can be elicited with a virtual limb that appears to be connected with one's torso than a virtual hand without an arm. In addition, it remains unclear if the avatar appearances linearly affect the detection thresholds. So it will be interesting to know how the detection threshold will be when the avatar is of medium level of realism, such as robotic virtual hands. Lastly, our recent study indicates when users use controllers for inputs, displaying the controllers instead of realistic virtual hands increase the sense of body ownership, even though they are objects. So the effect of showing the realistic virtual hands might depend on the input modality, and further investigation would be needed. To conclude, we showed that the use of realistic avatars instead of abstract avatars can improve the hand remapping techniques by making the remapping less noticeable without changing the mapping model itself. In addition, we show that the perception of the hand remapping may be related to body ownership illusions. I'll conclude my presentation with a take-home message. Be sure to use realistic avatars when you want to enable larger displacement while ensuring that their mapping is less noticeable.
Right. Thank you. Thank you, Nami. Great talk. Bunch of questions. First, I would say that it's quite interesting to apply detection threshold methodology to body ownership. I think it's great work and nice work. And a few questions. Did you use only right-handed subjects?
Yes, all the participants were right-handed.
So it might be an explanation for the shift you get only on one direction, no?
Sorry.
Could this explain why you have only a leftward shift in your data?
We actually applied both rightward and leftward shifts. So you mean that
you had only right-handed subjects, right?
Yes.
Okay.
And it could affect the anisotropy of the effect of rightward and leftward shifts. Maybe different results can be obtained when we try the left-handed people with and they use left hand, maybe.
Yeah, maybe. Another question is difference between a sphere and a hand. Would you get similar results with different something else? Somebody suggests a tentacle as an avatar instead of a hand, and in other words, is the sphere in itself a very special cue to detect deviations and shifts?
Yes, we consider it's interesting future work, and the reason why we tried with sphere avatar is that we wanted to assure that the same control, the users had same controllability with both hands when they push the button. So, but we consider the effect was because of the difference in body ownership illusions. So if the different avatar elicits a different strength of the body ownership, we consider that it affects the detection thresholds.
And maybe one last one. What about using, as you mentioned in conclusion, I guess, what about using the entire arm and not only the hand? Would it affect thresholds?
Yes, we consider that using a full body avatar will further increase the sense of body ownership and even further increase the detection threshold. But in case of the full body avatars, we have to take care that the connectivity of the arm from torso is maintained. If the arm is disconnected from the torso, it may damage the sense of body ownership, I think.
All right. I think we have to stop now. Thanks to all speakers. Thanks to Brooke. Thanks to everyone for making that possible. We did our best. And thanks to the audience.